In lecture 23, we learned about the most ideal thermodynamic cycles, and we called it as the Carnot thermodynamic cycles. Depending on how we use that cycle, we have Carnot heat engine and Carnot refrigerator or Carnot heat pump. Carnot heat engine is the most ideal heat engine that would give us the maximum efficiency possible. And how can you make this very ideal heat engine? Then Carnot cycle has four processes combined. The first process is reversible heat transfer in an expansion process from 1 to 2 that maintains its temperature at TH. Then it goes through the isentropic reversible expansion process that changes temperature from TH to TL. After that, the Carnot cycle goes through the isothermal reversible heat rejection and compression process that changes from state 3 to state 4. During this process, it maintains its temperature at TL. As a last process, it goes through the isentropic compression process, which is also a reversible process that makes connects state 4 and state 1. So in the TS diagram, it gives us a rectangle closed loop to make the Carnot heat engine. We also can draw the same processes in PV diagram as you see here. So again, from 1 to 2 we have heat transfer in, and 3 to 4 we have heat rejection. Now, how can we calculate the net work output as a performance of the Carnot heat engine? From the TS diagram and the old reversible process analysis underneath first law of thermodynamics, the W net out can be written in terms of Q in minus Q out. And if you apply this equation for the Carnot heat engine, we can express the net work output as TH minus TL times S2 minus S1. That in fact represents the area of the closed loop made by four processes. Also, we can express this W net out graphically in PV diagram, which also same as the area made by the closed loop of the Carnot cycle. We can calculate the efficiency of the Carnot heat engine, which can be written as this equation. So by knowing the highest temperature and lowest temperature, we can calculate the efficiency of the Carnot cycle. And what you have to remember is that should be the maximum efficiency of all thermodynamic cycles that you can think of. So nothing can exceed the efficiency of the Carnot cycle. Then how about the Carnot refrigerator or Carnot heat pump? So the difference between heat engine and refrigerator is basically in the refrigerator, we totally reverse the processes. So if you try to draw TS diagram of the Carnot refrigerator, then we still have the same rectangle, but it starts from TL, and we have heat input process. Let's say that is QL from 1 to 2. Then we have isentropic compression process 2 to 3. And we have isothermal reversible heat rejection process at higher temperature. So we have rejection of heat to warm environment, and there's 4 at TH. Then now we have isentropic reversible expansion process from 4 to 1. We also can draw the same shape in PV diagram as the Carnot heat engine, but the direction is reversible. It's basically the whole reversed in terms of the counterclockwise. Now we can calculate. We can apply the first law of thermodynamics for that Carnot cycle to calculate to get this equation. So the amount of work that we have to put into the Carnot refrigerator, that is W net in, can be calculated by QH minus QL. Many times this equation can be used to calculate QL for refrigerator. That is cooling load. Let me delete it, and cooling load. So that is the heat transfer we can take out from the space that needs to be cooled. Or we focus on this QH for heat pump, that is heating load. Okay, so that is our performance, then how much heat can be taken or how much heat can be supplied to the space. Also, equivalently, with what we discussed about the efficiency for heat engine, we also can define COP for refrigerator or COP for heat pump. And when you apply the Carnot cycle for refrigerator or heat pump, this COP can be written in terms of totally TL and TH. Again, that is the maximum COP of the refrigerator. Same thing can be written in terms of heat pump, but in that case, the desired output is QH, or in the Carnot cycle, we have TH on the numerator. So that is also maximum COP. Again, no real actual refrigerators or heat pumps can exceed those COP values for Carnot cycle. So with that being said, we basically can define the second law efficiency. We learned the first law efficiency. As eta th, or in the case, let me just try to use 1 to make it quite consistent. So first law efficiency is defined as desired output divided by required input. Okay. In addition to this very nicely the defined first law efficiency, we also can define the second law efficiency that compares your first law efficiency, like actual device, like actual heat engine or actual refrigerator or actual heat pump, to the reversible efficiency, like Carnot efficiency for heat engine and Carnot COP for refrigerator or heat pump. So by using this second law efficiency, we can actually see how far your devices can reach in terms of efficiency point of view compared to the most ideal case. By using the second law efficiency, also we can see what is more beneficial to invest your money in terms of improving the overall performance of your systems, either heat engine or refrigerator or heat pump.